Today, in this fifth video of the series, I want to introduce the language of chemistry. And I'm going to do it in this way. Language is composed of an alphabet. All right? We have so many letters in our alphabet, and we bring them together to make words. And then we string the words together in sentences, and then we put sentences into paragraphs and convey a meaning. In chemistry, we're working with elements or atoms, and we want to symbolize those atoms because the interaction of this atom with that atom, this element with that element, determines chemistry. So in this first slide, you'll see what the symbols that were used by alchemists in the Middle Ages to represent various ingredients in their kitchens, and the representations here are very cryptic to us because we didn't grow up with it. We didn't learn from the master as an apprentice. So they're not intuitive at all. When we arrived in the modern era, when scientists started to look into the nature of chemical reactions, they were looking for a way to represent what they were coming to realize were elements and atoms of those elements. So one of the first proposals was by John Dalton, who was the proponent. He introduced the atomic theory. So he wanted to represent elements as a collection of atoms. So he chose the circle. And the circle then he would modify with various letters, geometric figures, so he could distinguish among the atoms that he believed were interacting with one another to produce different compounds and subsequently chemical reactions. So we're inching towards an intuitive method of representing elements, although his was just one baby step past the alchemists. Wasn't very useful, although he did stick to it for his most of his life. What we come to next is the system that we use now, and this was proposed by Berzelius in 1813. That was his first publication in which he used this symbology for the elements. Berzelius was a Swedish chemist, and he had his fingers in a lot of pies, and he was able to isolate and characterize new elements that we don't have time for here. But his system simply used letters of the alphabet, and many of the elements are represented by single letters, and when that happens, they're always capital letters. The example here is hydrogen, H for hydrogen. Other elements, for instance, barium, could not use a single B for barium because the single B had already been taken by boron. So whenever we have to use two letters, Berzelius proposed that the first letter be capitalized, the second letter be small letter. And you'll also notice that some of the symbols bear resemblance to the English words for the elements. Hydrogen, obviously, barium, obviously, Ba, cobalt, Co. Lead, though, doesn't seem to resemble Lead. It's actually derived from the Latin word for lead, which was plumbum, which in Latin means heavy. So that makes sense. Lead was very heavy. So Berzelius proposed Pb from this word, and there are many other elements that follow that same pattern. Silver is one of them. Silver is from argentum. Okay, so we have these, the elements are represented by these letter symbols, and we still use that today. Um, Other examples, iron, Fe, copper, Cu. So we have to be very careful when we choose the symbols for our elements. If we say Co for copper, that makes sense, but it's not copper. Copper is Cu for cuprum. Co is cobalt. So it's still easy to get them mixed up, and I have to insist with my students that you be um, specific with your symbols, and I have them memorize about half the periodic table, which we're coming to in a few minutes. In fact, a few seconds. This is a copy of the periodic table that I distribute to my students. I couldn't find one that was just the way I wanted it, so I created this one from scratch in Microsoft Word. And what I've done is I've outlined in red boxes, not all of them, but about half of them in red boxes. Those are the ones I want my students to memorize because they are the most common elements that you will encounter in chemistry. If you're in the life sciences, I assume most of the students that are viewing this video are preparing to go into the nursing field or some medical field. You may not need all of these symbols, but you will definitely need those that are toward the top of the table, right? Especially carbon, nitrogen, oxygen, sulfur, phosphorus, and several others. So I would encourage you, if you're serious about mastering at least the rudiments of chemistry to apply to the medical profession, that you memorize as many of these as you can, if you haven't already. Now, we'll come back in a later video to the periodic table and tease out more information, because the periodic table is, I think the term is pregnant with information. And if you know how it's constructed, you can derive massive amounts of information about individual elements and associations of elements as well. All right. So the periodic table is organized in such a fashion that we can draw some conclusions about the behavior of the elements one to another. Now we're talking about chemistry. The periodic law is based upon an arrangement of elements such that the elements increase in atomic number from left to right, top to bottom. And their chemical properties also become periodic. Now, what we mean by that, if you think about periodic motion, maybe you've never had a physics course. So periodic motion, I'll define it for you, is simply motion that repeats itself. It comes back periodically. So I tell my students this, where you have a pendulum, and the pendulum swings from side to side. If it swings up and back and here, it's gone through one period of motion. So we apply that to the periodic table with respect to the rows. We have elements here and here and here, and they go on across to here. And we notice that elements in the periodic table can be grouped according to similar behaviors, similar chemical behaviors. So those groups run up and down. And if we continue to add elements in this period with increasing atomic number, then we come to a point over here with the noble gases where they seem to stop being reactive. But if we go one more to the right, they just instantly become very reactive. But instead of adding one out here, we take that one and put it back over here because it has similar characteristics to this group. So that's a period where you return to your original position. And we start putting in another period here across. So that's what's meant by the period, a period of the table and the periodic law. All right, there are several scientists that can be given credit, and I just introduced these for general information. You probably won't have to know them for the TEAS test. But Wolfgang Dobereiner, and this was starting in the beginning of the 19th century, recognized triads. These are groups of three elements that has similar behaviors, right? Like lithium, potassium, and sodium would have similar behaviors. Julius Meyer, Lothar Meyer, introduced the concept of valency. And we don't have time to get into that right now, but it just added to the bulk of knowledge that was leading us toward an arrangement that became the periodic table. The periodic table itself was proposed by a Russian, Dmitry Mendeleev. And he noticed these chemical and physical properties, similarities among the groups. So he grouped his elements. Actually, the first table was, his groups were left to right. But his second publication, he rotated them 90 degrees, and now they're vertical. But he also noticed that when he set these up in groups, these elements in groups, that the next one that was known to chemists didn't fit in the next group that it should have. Like if it was supposed to be here, it didn't share chemical properties with the elements above and below, but it did with the ones next to it. So he just moved it over one and left a blank. And not only that, he said, one day an element's going to be found that fits in that spot, and it's going to have these characteristics. It's going to have this atomic weight. It's going to have these physical and chemical characteristics. And he was right on every one that he proposed for a missing element. That's why Mendeleev gets the lion's share of the credit for the periodic table, because he used it to predict the existence of new elements. Now, the atomic number that later we recognize as the number of protons, and in a separate video I'll talk about the subatomic particles of elements. But for now, the atomic number was simply a number that an English physicist and chemist proposed with his laboratory work. And this fellow was in his early 20s. He was very young. And he was working with X-ray spectroscopy. In other words, he fired X-rays at metals, and he looked at the spectrum that they emitted. And he found that he could predict the frequency of radiation from a given metal in a formula he had devised. All he had to do was change one number. It was a whole number. 1, 2, 3, 4, 5. on up to 50, 60, whatever the case may be. All he had to do was change that number, and he could predict the frequency of the radiation coming from that particular element. It was always associated with that element. That was his concept of the atomic number. Unfortunately, Henry Moseley, notice he did this work in 1913. In 1914, World War I broke out, and Henry Moseley, being a patriotic Brit, joined the army, went off to war, and was killed in action. So that was the end of his career. Fortunately, he did all this work before he went off to war. Okay, the periodic table can be subdivided into areas. We've talked about the periods already and how they're horizontal rows of elements. We've talked about the groups. They used to be called families, but we're getting away from that and calling them groups. The vertical columns. And those elements in vertical columns have similar chemical behaviors. There's also a division in the periodic table between metals and nonmetals. And this periodic table is designed to show you that. If we draw a line between boron and aluminum, horizontal, and then stair step it, aluminum between silicon, silicon germanium, germanium arsenic, and so forth, that jagged line, that stair step, separates nonmetals on the right of the periodic table from metals on the left of the periodic table. And notice most of the elements in the periodic table are considered metals, and they share similar behaviors, similar characteristics, physical characteristics, not always chemical, but physical characteristics of metals. Whereas nonmetals, they have other shared characteristics. And some of those are physical appearance. Some of them are the way they behave toward one another. In other words, a metal and a nonmetal behave a certain way when they bond. Nonmetal and nonmetal behave a certain way when they bond. And we'll talk about that later also. Various groups have been named. The first group here is alkali metals. The lithium, sodium, potassium, rubidium, cesium, and francium. Hydrogen is not an alkali metal. We put hydrogen over there just for balance, because hydrogen in this period jumps over to helium, and those are the only two elements in that period. Helium does belong here because it's a noble gas. Alkaline earths are the second column. And then we go through a group called the transition metals. And then we get to the last six columns versus these first two. And this is boron doesn't have a name. Boron group, carbon group doesn't have a name. The nitrogen group are the pnictogens, spelled with a P. Pnictogen. And then oxygen are the chalcogens, spelled with a CH, chalcogens. And then the halogens and the noble gases. Then down here we have a group called the lanthanides, and that's because all these groups start with lanthanum. And actinides start with actinium. And these two horizontal rows actually squeeze into this place right here between lanthanum and hafnium and actinium and rutherfordium. We pull them out for two reasons. One is to keep our periodic table from being a mile wide, and the other is because there are characteristics of the way the atom is structured that can be deduced from these similarities. All right, so that comes later. Hopefully we'll be able to talk about those atomic structures and how to read the periodic table, but for now, that's enough. Okay, I mentioned these groups already, and the numbers of the groups here, this is an old numbering system, but it's useful. Notice 1A, 2A, 8A, 7A, 6A, 5A. If we go back to the table, we find these groups up here with rather than Roman numerals, we were using Arabic numbers. What they tell you is the number of electrons in the outermost shell of that element. So this group only has one, this group has two in the outermost shell, and so forth, all the way up to 8. And that leads us to a discussion of the octet rule. You may hear that. You probably have heard that. If you take a biology course and they touch on chemistry, they'll talk about the octet rule. But this is where we can glean that from these first 2 columns and the last 6. Transition elements are a little squirrelier. These are the A groups, and these are the B groups down here. Also, you may hear of these 2 columns and these last 6 columns together as representative elements. I don't know where that name came from, but just so that you know you've heard it before. Okay. And here's another representation of the periodic table. I don't see anything outstanding here except for what can you get from the periodic table. If you look at individual elements like carbon, that 6 is always a whole number, and that's the atomic number. This number here is always a fractional number, and that's the atomic weight, or the mass number. It's not the mass number, the atomic weight or the molar mass. And it's useful, and we're going to touch on that later. But this is the information you can glean from this very simple table. Some periodic tables have a lot more information in each of the cubes, each of the squares. But this is a very simplified. Another thing you may notice is some of these elements have parentheses around their atomic weights. If the atomic weight is a whole number with the parentheses, that means these elements are radioactive. And this happens to be the mass number that is the most stable isotope. And I'll have to define what that means later also. But now we have names for every element in the periodic table, and there are 118 of them. The last one is here, over here on the right. Let's see, I think my periodic table has a name for that one. Yeah. Let's see, that's, oh, I've forgotten what it's called. I know TS is tennessine. OG is, I want to say organicine. Anyway, for a while we substituted a placeholder in there. Now they all have names, and that's as high as we've gone with naturally occurring elements or man-made elements. A lot of these elements are man-made. Okay, so I think that's the end of our discussion for this video, and we'll continue building on what we've learned today. We've learned the alphabet for chemistry. Then we're going to eventually put those letters together and make words or compounds. And then we're going to put them into a sentence, which is a chemical reaction. And that's where it really starts getting interesting. But for today, that's all I have for you.